the topic of my presentation is very important, very interesting as well, and we're speaking once again about yeast. Why yeast? They are the main characters of this process, the winemaking process. We need yeast and we need grapes. Living yeast for fermentation. It is used for the fining process, and it can be used in different ways as a technological adjuvant. When we talk about yeast protein extracts, we are talking about this topic, and we will discover, as we are already doing, the several characteristics that this mechanism gives us as a technological intervention to improve the vinification of different wines with different organoleptic characteristics. So, yeast protein extracts, or YPEs, are a product that have to comply the regulations of the OIV, of the European Union. So when we talk about YPEs, we have to talk about the regulations of the organization, the international organization. If we see the prescriptions that they need to have and its applications, they are quite generic. We have clarification, we have the interaction with phenolic substances and tannins, and the selectivity, the selection. We also talk about clarification. In the regulations of the OIV, topics are quite open. Here we have the English version of both resolutions. I remarked a mistake in the English version because they're talking about racking, and it's not clarification. We're talking about clarification as a term itself. So these possibilities need to be used in the enologic chain to optimize a product. First of all, what is the law of the OIV to approve a wine? The aim of the organization is to reduce at its maximum the animal origin products. This is an initial point that led to the admission of these techniques. We're talking about products rich in proteins, produced by yeasts with concrete characteristics, depending on temperature, pH, and yeast strain. So, they are protein-rich products, and this can change depending on the process of production and their characteristics. These products are mixed preparations and complexes for enological purposes, and they are very difficult to manage if we want to apply accurate winemaking. So we know that using autolysis, our colleagues from the University of Dijon already told us regarding autolysis of yeast, we have different substances due to the enzymatic activities. We have an enological impact that is significant. The cell walls, we have polysaccharides and glycoproteins, peptides and proteins are extracted that are the target of these products. So we also extract aromatic substances I did my Erasmus when I was a student. I learned that the aromatic part is very important. In particular, it comes from the nucleotides and nucleosides. They are very important because the aromatic impact can be very powerful for good and for the bad. Then we have some softness characteristics linked to glycoproteins and proteins. We have to have in mind the enological objective and the side effects. And this is applicable to all complex products. So be careful with the side effects. The positive part, according to the OIV, we have a minimum of 50% of protein fraction with a specific molecular weight. This has to comply with the International Enological Code. If we read attentively this code, we see that it's not a pure product as the animal gelatin that was the initial reference benchmark. It's not a pure product, so we have to treat it in a different way. Considering the objective of eliminating polyphenols or astringent substances, they're different things and they don't always coincide much. Depending on the scientific experiences, we need to have the tools in order to conduct a very deep analysis of these substances, that they hold very good opportunities. But I repeat, be careful with the side effects, that they can be positive, but we need to be aware of them by analysis. Our French colleagues have wide experiences with these products. Here we see the percentage of proteins. We see that almost or more or less 50% are proteins. One important aspect is that we are trying to think in terms of adjuvants, and that they have a colloidal state once they enter into the wine state. But the complex molecules interact. Here we see the experience of our colleagues from the University of Udine. This gave us colloidal stability. In this case, we lose aroma, and we need to perfectionate these techniques in our vinifications. Here, numbers from University of Dijon, clarification effect, very interesting. Effects on the protein stability and heat tests. A huge effect on wine filterability. And they can reach 60 grams per hectoliter of these dispersion products. Here we have the kinetics of decreasing. They're very interesting as well. And the dosage is not always giving us a decrease, a linear decrease of turbidity. This means that we need to have tools to have the right dosage, depending on our objective, reducing costs and so on. And in order to make this balance stable. But what do we need? Not to decrease the red tonality, specifically for varieties whose polyphenols are not excessive, for example, Montepulciano d'Abruzzo. We have seen a relationship between the modification of these products. The University of Dijon also studied the ethanol index, and it is a very useful one for evaluating polysaccharides impact with these products. And we see it increases as soon it increases as well the dosage of ethanol, so it can be an effect of monoproteins of the product. Regarding the sensory aspect, we need to consider it because the impact or the colloidal interaction that we've seen a while ago, the final balance is that it has an effect. The vegetal, the fruity notes, by the proteins in this case, are reduced. Therefore, fruity notes are limited that sometimes don't go towards the consumer taste. We have roundness, fullness in the mouth, softness, and an improvement on characteristics. The wine is clear, even though it has colloidal particles, and the aroma that interacts with these particles remains stable. The olfactive peak is reduced slightly, but we can see that it remains stable. Here we have different experiences in the scientific literature. Here we see the interest of 3 YPEs, and we can see, apart from the effects on turbidity, we see in the red table very interesting results, and I will talk about them later on. And it has to do with isoelectric points. This implies a modification on the electric charge of the system, because the proteins of the wine have a positive charge, the pH of the wine, but here we have opposite values, and one can think, why not? If we have a negative charge, even though the electric charge is not the only phenomenon, we could use them for protein stability. Other experiences in substitution and replacement of animal adjuvants such as pork gelatin, we have very interesting results related to bentonite as well. Turbidity is reduced and color remains stable, specifically for red wines. We don't need to extract color from red wines. We can eliminate astringent tannins, and here we see the best moment of application and the quantity. Experiences from Enopia group show what I was saying about the isoelectric point. The value of zeta potential is negative. In the left part, you can also see the value of the diameter, the hydrocolloidal diameter of the particles, lots of nanometers and 1 micron, and a huge variety of colloidal particles. I remind you that if we have the same weight in dry of one colloid, we have one specific surface that can vary, and it can be very wide. Here we have a zeta potential that is negative. I don't know if in your laboratories you have this possibility of measuring zeta potential. And finally, we have assessment colloidal structure parameters of our masts and wines, as well as our adjuvants. These are the analytic systems that are already used in concrete sectors, and they are up to date, definitely. They can be very useful for our sector as well. Other differences compared to the use of gelatin with the same authors, interesting effects on protection against oxidation. If we study these effects on laboratory, this is one thing, but if I want to use it in the winery, I have to pay attention to the rest of aspects and elements. Here we see the results about the phenolic stability and a protein stability as well. We will talk about that later on. Other experiences talk about the protection of color, and this is an essential element regarding red wines, as we already mentioned before. Regarding enzymatic activities, we see clarification kinetics improved in animal origin substances. These are products proposed before the resolutions of the OIV. They are products that are very interesting, but we need to get to know them very well in order to be able to implement them to our specific situation. We need to know the side effects as well. Some of them can be positive, as the aroma interaction and more stability, but we can have them negative as well. So we need to analyze them in a deeper way. But what is the application target of these products? The must and the wine, of course, as the OIV states, and we need to do tests, small-scale ones. They're not always feasible, but when they are a very good tool to assess our products. One small-scale test helps us to identify the dosage, the ideal dosage, to reduce the inputs. Another important aspect is complexity of protein extracts. All enterprises, from a practical point of view, manufacture mixed products. We were talking yesterday about chitosan, but we will talk about more adjuvants. Be careful, we have to conduct small-scale quality tests to avoid risks. Because once the powder product is dispersed by water or wine, I cannot exclude risks, reaction risks among two products, for example. So we need to apply tests to know the behavior. And here we have the colloidal system. Yesterday, Boss already talked about this topic. We have tools to measure the zeta potential of these products. And this is very important to see the electrical situation around the colloidal part. Our inactivated proteins of the wine have a positive charge. We've seen that they have a very low isoelectric point, and we can think about a negative electrical charge. And here we see
la cuvetta rossa che vedevate prima era la cella di misura durante la misura del diametro.
We were seeing the measurement cell of the particle's colloidal diameter. Here we have again, okay, the measurement system. Here we see the effects of the dynamic light scattering technique. That way we can measure the quantity of the electric charge in order to manage the stabilization and clarification techniques. One difference of 0.1 or 2 in terms of pH can change drastically the electric charge of adjuvants. We did this with the monoproteins with an electric charge about 0. So we saw how a change in the MLF can change the charge, for example. These measurements are techniques that are potential and that are feasible to optimize the knowledge of products and its implementation in the vinification techniques at different levels. Here we see two extracts, two yeast protein extracts, and we measure the zeta potential by the ELS, the dynamic scattering. It is measured in a non-destructive way. One important aspect is the speed to obtain analytic controls. Here we see two protein yeast layers and they are negative according to the data of Onapia group that I showed you before. Here we have different values from the previous ones, always negative ones, and as a comparison we can see the color of the zeta potential of a pork animal protein to say that this is a very sensitive system. This could become a control quality daily system to define guidelines, quality guidelines for these products. We have these systems. The negative value confirms that it exists, the isoelectric low point, below the pH of the wine, as we already saw a while ago. Using other tools, we can measure the potential, the streaming potential, in order to measure the electrical charges. And we see that we have a product with chitosan where we can see a positive charge, a very high one. This is a charge balance, and we see how chitosan contributes. It's a mixed product. For example, the fact that it's very important to measure mixed products and its characteristics. This is another example of diameter particles in one layer of yeast, protein yeast. We see homogeneous and big particles that could be suggesting one activation times increase. Colloidal systems in the wine belong to the colloidal stability system of the wine. So we've used this product depending on the low isoelectric point as a deproteinization product, making the most of the native proteins of grapes that are the most unstable ones. Here we see the comparison with an animal protein. We eliminated the 24%. We have a wine, Pinot Grigio, it's very unstable, and we eliminated up to 61% of proteins. We did this with a test of protein stability based on the electrical charges. And we specified the positive charges. The final point about the 61% is analyzed hours, when some hours after this process. This means that we need to consider a determined optimization time, 7 hours more or less, in order to reach the optimal point of the result. What does this mean? This means that potentially, apart from the generic indications of the OIV about clarifications, why don't we use this product as well as an option for stability, protein stability of white wines? This is just with the purpose of adding one opportunity for the enologist in the winery. We could decide if we use bentonite or if we use aspergillopepsina 1, that we all know it's a protease that needs a thermic process of 70 degrees during 1 minute in must or wine. We need to be aware about the potential aromatic risks. This is a critical point for me. Another opportunity, and I thank Professor Morata. He was talking about other processes. Our Spanish colleagues, what happens about ultrasound? When we use the must, the grape must, we are seeing that something is happening to proteins. Reactivity is increased. So we see that maybe if we apply ultrasound, potentially we can apply a type of protein stability. So we're studying these molecules up to detail to optimize the use of ultrasound. This is interesting. We see how the YPE is an adjuvant. Aspergillopepsin is biotechnological. And we see how the enologists can choose one or more techniques. Usually we're used to choose one technique, but I think that to reduce inputs in the winery, we can think about synergies between techniques with the objective of quality. We need to carry out tests, and we need them to be based on different criteria. What is the sensory impact? We just need to smell the yeast layers in order to perceive different odors. Our French colleagues have experimented with yeasts, and we saw hundreds of compounds. So it's a very strong impact. It can be positive or it can modify the sensory aspect. If we do small-scale tests, we reduce the quantity and we optimize our aim. We will do tests ad hoc, and here we have different examples for the laboratory. We can do quick tests. I really advise you to use them because that way we optimize our enologist system. We can apply accurate enology thanks to different treatments. If we know the enologist target and the length purpose of a wine. Accurate enology means knowing all techniques to customize them in the same deposit or as well directly in the procedure. We need to carry out a continuous assessment. Therefore, we have high expectations regarding YPEs, and we need to know our aims and the side effects to limit damages. Let's remember that side effects can modify the aroma profile of the wine, so it's important to carry out tests at a small scale to optimize the product. Thank you so much for your attention.